Well, I have a very nice twist to report. I've been studying magnetic amplification, and there was this site up here that I went to some time ago, and I revisited it because I found that Wikipedia has something to say, not only an article on magnetic amplification, but also on saturable reactors. And then I found this link that was dead on Wikipedia. I think it was linked in this article. So I went to archive.org and I got a fresh new copy. Um, and then I downloaded it, and it's a very nice PDF file on magnetic amplifiers by Paul Malley. And it's worth preserving. It's worth, getting a hold of it. It says that the origination of magnetic amplification dates back as early as 1885, although they didn't call it that because they didn't recognize what it was. But they used it in theater lighting, of all places. So I guess, and it was patented in, I don't know, 1901. So I'm having a hard time finding out who invented it. So I guess originally it's ascribed to no one in particular. So I instigated it in a circuit. Let's refresh this. Let's close that off. And let's go get the mag amp. So I put it under unknown inventors. And the only deviation I did was, well, a major deviation. I took out the AC source over here, and that made the lamp the farmost component to the right of the circuit. And then I put in two low-level capacitors of 1 picofarad each instead of 2 wires. And then I reduced the henries on the inductors down to 75 nanohenries, and I estimated, this is, my guess because I was having a hard time figuring this out, trying to figure out what this fellow here, what inductance he uses. All I could determine was a 40-to-1 difference in voltage. So using the formula that you square the inductance to find the, excuse me, let me say that again. You square the voltage, and then that becomes the ratio between your two inductances, between your primary and secondary. I got a 1600 ratio by squaring 40. And then I had a guess estimate based on the resistances I discovered for shopping around on the internet for mag amps. They had a resistance cited as 300 ohms, and using the, again, speculation that a coil will have a resistance in series inside itself 4 times the units of henries. So I decided, well, if it's 300 ohms, then it should be 75 henries. But it didn't help trying to get a surge out of it. I had to put in these low-level capacitors and then reduce the henries down to 75 nanohenries, which doesn't surprise me, because a lot of my earlier circuits, I had to have 1 picofarad for the capacitors, the 2 capacitors in the LMD module that I was testing, and I had to have something like 10 to 100 nanohenries on a 1-to-1 ratio transformer. So here I put 75. I just, picked, I went by factors of 1,000. I kept dividing down until I got results. So I put 75 nanohenries on the primary over here on the left, and that means that the right-hand side is very, very low. As you can see, I've got 150 plus 150 nano-ohms resistance on this side, making 300 nano-ohms, and then the combination of these 93.8 pico-ohm resistors that have to be added together, so that's nearly 200 pico-ohms on the right-hand side. And then I put in the diodes just like he specified. Of course, the capacitors he doesn't specify. And this kind of wiring configuration. And I even had the pot, the potentiometer in place, and I have it scaled down very low to 219 ohms on R1, and I think it looks like 787.1 ohms on R2. Then I had to lower, the last thing I had to change to get this to surge was I had to lower the voltage on the DC source down to 1 microvolt. Now, I don't know, I kind of picked an arbitrary value because it was up at around 12, which is what this link specifies, around that ballpark. But it wasn't helping the surge, and of course, to occur because a voltage source acts as an anchor weight. A voltage regulator, in normal parlance, I call it an anchor weight, because it holds back surges. That's why I had to get rid of the AC source over here and lower the DC source over here. Now, I put a resistor here of 100 mega ohms to put a clamp on the amperage so that I don't lose too much in the course of running this circuit. But it didn't matter. You notice I have no scopes down here. You know why? This is why. Because it immediately goes to non-infinite matrix. Sorry. Upon turning this on. It's one of my quicker explosive surging circuits. I only have 2, and this is one of them that you don't have to wait. It's right away. But this one is, I think I have 3 now. This is the 3rd one. And unlike the Pierce Arrow variety, this one actually lights up. Actually, I have 2. This is the 4th one that's immediate. Well, no. No, I think I only have a couple that are immediate. Anyway, like one of the Pierce Arrow explosive circuits doesn't light up anything. It just gives you the non-infinite matrix error message and shuts off immediately. Well, here I actually light up these wires and, you know, this side of the resistor. So it shows it had a chance to put some power in. And the way we find out how much power is in, we pick a component, doesn't matter, it can even be the text, and you open up its edit dialog box, and then you save it by hitting OK, and that should bring back, that erases the error, the frozen condition, and now we can put our cursor over any component and see what's accumulated there. And look at that. Power is infinity. It has a little infinity symbol and then YW. Infinite power. Infinite power, and it didn't even get a chance to heat up the lamp, so it's still at its coldest caloric index of color index of 300K. That's temperature is how they rate the color index of a lamp. They use color index, and it's in 300 Kelvin. You know, that's how they do it. So whatever that means, I don't know, but that's the way they do it. So it's the lowest. It's the default. And the capacitors, same, infinity. And the capital Y is either Yoto or Yokta. I think it's Yokta, because Yoto or Yota is 10 raised to the negative power of 24, while capital Y, I think, is the 10 raised to the positive 24 scientific notation, and I think that's Yokto. Anyway, I don't commit these to memory. I'm not very good at it. So that's all I get out of this. Kaboom. Okay? So I call it is.gd/mag_amp because somebody else already took the mag amp, all one word, so I had to create a deviation. And then that was yesterday. And then today I decided, okay, I'm going to try and see if I can create a variation on that that doesn't blow up in your face. See, there's no pound symbol down here in this one. The hash symbol, the pound symbol, means instantaneous Overunity, namely kaboom. But this one, I don't have that because I managed to get it to slowly escalate and turn it into a power supply suitable for an AC motor along the same lines of reasoning of Pierce Arrow. But this is better. Better because it puts out a true AC sine wave on the inductor. These are the two scopes, and here's the inductive load. A true sine wave at around 240-ish kilocycles is the sine wave, Now, the time frame I have here is 1 nanosecond. I had to go down that low because I had convergence error problems. You know, whenever you get convergence error problems, it means the simulator can't keep up with the time step doing all its calculations. So all you have to do is keep lowering the time steps. Just slow it down to give it a chance to keep pace with all the rapid changes that are taking place. So I had to lower it down to 1 nanosecond. You know, I did it by factors of 10 until I got safe results, namely results that didn't error on me and freeze up the simulator. And then I added in an IV, or is it VI, a VI mapping, so we can see whether or not there's a negative resistance taking place, and I believe there is, during escalation. During cruising, that's when the sine waves appear, and that's when this V divided by I mapping turns into a wholesome round circle, indicating that there's no negative resistance happening during cruising phase. It's just a standard conventional operations. See if we go here. 90 degrees phase relation. Amperage is out of phase with voltage by 90 degrees. I don't think so. No, none of these apply. Mild reciprocal resistance. No. Distinct reciprocal resistance. Yeah, the snowflake. That's during escalation mode. Output exceeds input. Well, duh. Overunity and free energy. Yeah. Non-instantaneous kaboom in this case. And I have no circuit information. As you can see, I don't have anything to offer for extra information. All of it's right here. So you can go to this website and look at that PDF that I just showed you. This nice one. Or you can go to... this one brings up this circuit in this simulator, in this JavaScript simulator, and this link brings up the circuit mod Java version of Paul Falstad's simulator. It's just a text file, so you have to download the software and install it on your computer. And I have copies on my download link section. If we can go there. We go to Vinyasa circuits. No. Is that where we go? Oh, I'm sorry. No, that's not where we go to. Sorry. Well, we'll just wait for it to load. It takes a little time. It's a PHP file loading in all the files of that directory and a customized listing. So you can download the files, you can run them in the simulator, or you can download Circuit Mod. Here's the download link for Circuit Mod if you also have Java installed on your computer. So let's go to the parent directory, and then we go to zipped files. That's it. And now we have, where are they? Here they are, exe. So we have 2.6 and 2.7. 2.7 I'm not very pleased with. I'm not at all interested in. It's like, you know, kind of yucky. So I went back to 2.6. I was happier with that one. Neither one is perfect. It's not as good as JavaScript in the sense of drafting. I have to draft in JavaScript and then transfer it over to the Java version and then make tweaks, mostly in the text, because it's not very user-friendly, the Java version. But it does, I think, run more realistically. It's more stable. It gives a very nice output. JavaScript tends to be a little weird in some respects. And in that sense, its weirdness is an advantage for me because it makes Overunity surge-oriented circuits easier to craft. So the real test comes when I take it out of JavaScript and try to implement the same circuit in some other software-based electronic simulator. And of course, the first one I pick nowadays is Circuit Mod. Since it's the same Paul Falstad simulator, it's just in Java software language rather than JavaScript. Of course, don't expect it to work in other people's softwares because they tend to have agendas to suppress, to prevent or make very difficult your crafting and running a surge-oriented circuit. Because in today's world, we have a hypocritical attitude among electrical engineering and physics. Namely, on the one hand, they'll deny that surges exist. You know, surge circuit is just another name for Overunity. So they'll deny that Overunity exists on the one hand. Yet on the other hand, they are very active in suppressing surges at the outset by way of prevention, mostly. They're taught how to prevent it, and if it should arise, what to do about it, because they don't get paid by whoever's employing them if their circuit blows up or fries or melts. It doesn't matter whether you're into power supplying, specialization as an electrical engineer or electronics engineer, or if you're into digital electronics. Either way, whatever. Nobody wants their circuit to blow up. Well, if they don't study it, to study how to manage it, of course it's going to blow up. Now, this is a very simple circuit. There's no automatic safeguard to prevent blowing it up. You have to manage it. The operator has to manually manage it. And you only get two choices, and it's all in this switch right here. It's closed right now, so when you turn it on, it'll increase the power supply, but there should be some clutch, an automatic clutch, to disengage the motor coil, this thing over here, because it'll probably lock up suddenly if you're already driving and you want to escalate your power supply. You want to build it up because you're starting to slow too much in traffic. Let's say you're cruising on the open highway, let's say. We don't want the motor to lock up. So there has to be, somebody suggested the use of flywheels in multiple gimbals to transfer the kinetic momentum from the motor to some other rotating component of the system, so that the motor can come to a complete stop and the car can stop at a stoplight or a traffic light, or if you immediately have to come to a stop, you don't want the motor to lock up or the motor to become damaged in any way. So there should be some safeguards, but this simulation doesn't cover any of that. It just covers basics, the conceptualization of what I'm trying to do is to at least show that it's possible to make it usable in the real world, if perchance it can be buildable. We don't know that yet. Nobody's built this particular circuit yet, and I certainly haven't, and I don't have the means or wherewithal to do so. All I can do is simulate, because I won't tell you why I get into that. Anyway, so the motor impedance, the motor coil represented by the single coil, is very large. It's 1.4 mega ohms, which just happens to be the square root of 2 times 1 million, accurate to several decimal places. And that's kind of interesting. I don't know if it's valid assumption on my part that that's what it is exactly, but when I did the division of voltage divided by amperage on this coil, that's what it came out to be. It was kind of surprising to me. Now there's several features here. This analog switch and this analog switch are not tied to any timer. You see this white little bulb here is not tied to any wire, and the same thing here with this white ball, which would have regulated them. So instead what they do is they pop open immediately upon turning this on. So this will pop from the ground to the aerial, and this will pop open to disengage the battery, to safeguard the battery from wasting any energy. You can use this scope to see if you wasted anything, and you don't. And here I pop it over because, of course, if this is going to be in an EV motor situation, it needs to be portable. So I'm imagining that if you start up the car in your garage at home, you have to have it plugged into a ground, not to the grid, but to a earth ground, a solid earth ground, just to start up the power supply. And once it's started up, it'll switch to the aerial, and then you can run it all day long if the power supply does not lose any juice in the course of any of your stopping, on errands or at work. You park it, you turn it off, but all you've done is turned off the motor and the power supply is still humming. Unless, of course, you have a manual override that switches you back to earth ground after you've plugged this in to a grounded outlet. Excuse me. And then you could restart it again from a cold start using that ground, because the earth ground, you can use either one for starting this and running this. I opted to use both. Of course, if you use the earth ground, then you need the, even though it's a low voltage, 1 microvolt, but you need the DC battery to get it started. Otherwise, if you don't use the earth ground, you can use the aerial and get rid of this battery. But I chose to do both because I found that if I eliminate grounding altogether and just depend exclusively on an aerial, some of the outputs are negative and one is positive. I believe it was, no, I can't remember now if it was the lamp or the inductor, but the voltage was positive and everything else was negative. You know, the lamp amperage and voltage was negative, or else the inductor was, and then the other one was just the amps was negative. Well, I wanted everything to be negative, and so to ensure that, I had to start it up grounded to the earth and then switch over to the aerial. Once the polarity is set up, it won't deviate, at least not right away. And I haven't tested this a whole lot, as you can you might gather from the way I'm describing the situation, but I have done a little bit of testing. And so I chose this setup because I wanted everything to be negative. I didn't want anything to be positive because I wanted only negative ions to emanate from this device, especially from the aerial, because negative ions are healthy, they are refreshing, they're similar to the atmosphere after a rainstorm, or if you're standing by a waterfall, or if you're walking around in a forest of trees, because you don't want positive ions to predominate, or else you'll be encouraging, you'll be supporting chemtrail dusting of our planet, because they only spray chemtrails when the air has a positive charge to it. Then they know the dust will hang in the air. And also the humidity has to be a minimum of 70%, because they want to draw the humidity of the earth, away, the ground, away from the ground. And you won't notice anything while they're spraying, but once they stop after a series of weeks or months of spraying, you'll notice forest fires break out, you know, like in the summertime, heat waves and forest fires, because the ground is so dry, because they've dried out the earth. But they won't do it unless the air is positively ionized. And so we want to counteract that and have healthy air. We don't want smog, and we don't want dust hanging in the air, or smoke from factories or from other cars running on internal combustion engines, or chemtrail dust, metallic filings and whatnot hanging in the air. We want everything to fall out of the air, and the only way to ensure that is to drive around in a car that puts out negative ions. Now, we don't want the aerial to put out local radio interference, and so there's some other pieces of information that are lacking in this particular file that I've covered in a lot of my other simulations, but I haven't done it here yet. I could include that. I could include a circuit button that gives you information on ionization. I think I'll do that. So that's one thing I'll change after I get done taping this video. And that tells you some of the basics of converting your aerial out of radio transmission into an ionic generator, because that's what we want the aerial to do. The aerial is not getting energy from the environment. It's simply serving as a reference, and that's why it's mutually exchangeable whether or not to use an aerial or a ground as a reference. So this could be a power supply for a building, and then you can dispense with the aerial and just use an earth ground, and then you don't have to worry about local radio interference, because you're pumping all of it into the... You're creating all of the disturbance in the earth rather than in the air. And since nobody uses ground radio, only people like Eric Dollard, right? His seismic research, but most people don't do that. And so it would be more suitable, if this is a power supply for a building, to use earth ground rather than an aerial, and that means you'll have to have this battery just initially to start the thing up from a cold start. Once it's started, you don't need the battery. And I took out the potentiometer here because I didn't need it. What else did I do? I think that's it. Yeah, in terms of modifications from the prior mag amp circuit that I did that blew itself up instantaneously, you know, I didn't do a whole lot of changes. So when I took out the AC power source over here on the right, the lamp became the rightmost component. And then I disconnected it from the bottom leg and chose to connect it to either earth ground or an aerial. And of course I put in these two 1 picofarad capacitors, and I lowered the inductance on the two transformers. So I didn't have to do too many changes to make this thing work. Now let's try it out. So we start it up, and immediately it pops over to the aerial, and the battery pops open, disconnecting the battery. And you see already it's surging in the negative direction. And our V over I is showing negative resistance here. So we'll pop this open. And now we see that the inductor turns into a nice, casual, smooth, well-defined sine wave. And in a moment, we'll find out what the RMS is and the frequency. The simulator, there it goes. So we've got an RMS value, and we've got a frequency value. And that'll only happen if it's a clean, distinct, singular frequency. I've noticed that in a lot of my simulations, I would try to get the frequency, and I couldn't get it, or RMS, and I didn't know why. Because my output was spiky, random, densely populated with random spikes of varying amplitudes at varying intervals in time. And so there was nothing for the simulator to average to find out what an average figure of RMS and frequency is going on in that component. So this is like the first, one of the rare, not the first, but one of the rare instances in which I get a readout of this sort. And it shows that, again, just like the way it looks, it's an AC sine wave capable of powering an AC motor. So this coil here can represent a single-phase induction, or you can use a rotary generator to convert that into use for a three-phase inductively winded AC motor if you choose to use that. I mean, you can do whatever you like. Now the lamp is all heated up at a very high Kelvin of color index, but it's slowly going down because it's disconnected. The switch here is disconnected, so we're not even using the aerial. But it looks like the aerial might be charged. Yeah, there it is. It's got 10 volts, which is not surprising, and its amps is 1 nanoamp. So once it switches, this is why I like doing this, once it switches over to the aerial and then it switches out the aerial, you're not really putting out any radio interference. So probably it'll never happen, and so we probably don't have to. So everything I said about an ionic generator may not be needed, may not be necessary in this instance, but we do need a reference, and the aerial and the ground serve as references for the circuit. But it's in cruising mode right now, so it's not pulling any juice. Now if we close the switch, you'll see that now the aerial is running in the negative megaamps. So when we're escalating, we're putting out a lot of radio interference. So it's only when we escalate that we have to protect our local environment, so the FCC is kept happy and our neighbors are kept happy. Whoever we drive by is kept happy when they try to get AM radio reception, or maybe even FM, or maybe their TV doesn't work, or will work without static interference. Sorry. We do have to have that protection in place when we escalate the power supply. But when we're just cruising, it's not a problem. But cruising, for any length of time is usually on the open highway, and there are no buildings close by unless you pass businesses on either side of the freeway. So ironically, the real problem is stop-and-go traffic in the city. And so, yeah, we would need an ionic generator. I forgot about that. During the escalation of the power supply. When we're pulling away from a stop, if we need to power up the power supply. If we're simply disengaging the motor and the power supply is still humming, we might be able to ease in, with certain gearing, so we don't lurch forward very suddenly and give ourselves whiplash, go from 0 to 60 in an instant, probably burn a lot of rubber, So, I mean, there has to be some accommodation, obviously. Unlike my Pierce Arrow circuit that uses, where was it? That uses switching. Which depreciates it drains out the power supply when you're sitting at a stoplight or something, or a stop sign. Let's see, where is it? It's not PA for the real world. Here it is, switch PA. So this has a switching arrangement here. Once you reach, let's slow down this because it's jumping. Once it reaches a certain power level, which apparently will take a little time because I had to slow it. There it goes. It's starting to rise. Slowly. Sorry. There we go. So the aerial is showing some negative amperage that's accumulating, getting higher and higher. The resistors surrounding the motor represented by these transformer coils, they're rising in amperage. So then when I turn off escalation so that it's just cruising, there's this big, huge surge, engaging that switch. And then it immediately starts to die down. In this case, it's still dying down. In this case, it's also still dying down. So it takes a while. So what was the point? Oh, so this is cruising mode, and the aerial is eventually, I think, going to go to 0 because it's disengaged, right? No, it isn't. No, it's the capacitor that's disengaged. The aerial is still engaged, so the aerial is still going to put out a charge that's going to disturb the local environment if it's not ionized. So this one needs ionization of the aerial all the time, while the other one that we were just looking at, see, look at this, it's already down to nanoamps in the negative. So that's not a disturbance to the local environment. It doesn't take too long to reach that point, but before it reaches that point, there'll be a momentary surge that everybody will hear very loudly on their AM radio. It'll be like a kaboom of static, and then it'll quickly disappear, and people will complain. If you're the only one driving around, they'll locate you. They have means to triangulate and locate the disturbance and put a stop to it by raiding your place and take everything, including your socks. So we don't want to get the FCC angry. That's the last thing we want to do. So whoever invented this beautiful circuit, it's quite this magnetic amplifier circuit. It's quite a dilly of a dally of a circuit. And the other nice thing about this circuit is you don't get a big, huge surge when you pop open the switch and switch to cruise mode. It just immediately goes into an AC sine wave, which is ideal. It's acting as its own snub to prevent any kind of surge from occurring when you switch from escalation of the power supply to cruising mode, coasting on stored electromagnetic potential. Am I saying that right? Electromagnetic momentum within the circuit. Let's see. What was the other thing I wanted to say? Well, let's try, doing what I haven't done yet. Start and stop the escalation process. So there it's escalating, and now we're going to cruise some more at a higher value. So here you see it's megavolts and amps versus amps. So the motor has to be able to tolerate high voltage along with whatever amperage is your target for running your car at. Or the inductive load in your home, if this is or the non-inductive loads for that matter. I don't know how this would behave with a non-inductive load, but we all have inductive loads. It's mixed. We have the compressor motor in our refrigerator, and then we have the AC and the heating unit in our building to force in convective air, a fan to force in convectively move air into our living space, either warm air or cool air. So, and then the lights are non-inductive. They're resistive loads. So we have a mixture, and so I don't worry about, I just, I would leave this here. But we get a nice clean sine wave, a little high of frequency, but I was watching a video of Donald Smith, and he was saying 60 cycles is the worst for health that we could have chosen. You actually have to get up above, was it 400 cycles a second or 4,000? I can't remember. Before you start seeing overunity automatically happen just by choosing a higher frequency for an AC power supply. And also, it's healthy. It doesn't hurt the body when you get up to higher frequencies. As I recall, I think 1,000 cycles per second was the cutoff. But I read that elsewhere on the online some time past, I don't know, a year or two ago. So maybe he was quoting 400 cycles a second. Maybe that's the distinct cutoff. So that's pretty close to 1,000 cycles per second. So, but pretty close to agreement between the two sources of information in terms of what's healthy to live in an AC field, because we do. We live in a not a Faraday cage, but the inverse of that, in which we're surrounded by wires that are creating an AC field that we live in when we're inside our buildings. That's why I like to be inside my DC-oriented electric car when it's running, because it's a very highly influential, beneficial influence of good health to be in a DC field rather than an AC, because who has high-frequency AC power supplies? They just don't exist, for all I know, for the most part, from the consumer's point of view. We just don't get to use those. They're highly specialized industry probably uses them, but us, the consumer, we don't. So instead, we're bombarded by all these unhealthy frequencies. There's a road in Europe. If it's getting close to sundown, and so you have long shadows, and if you drive at 60 miles an hour, the shadows, they have trees planted on the west side of the road, the shadows will hit your eye at 60 cycles a second if you go at the right speed. Maybe it's not 60 miles an hour, but it's a certain speed. The tree shadows will hit your eyeball at 60 cycles a second, from your side view, your peripheral vision, and it has caused people to lapse into a state of non-consciousness. They black out, and then they cause an accident for themselves. So 60 cycles is not at all healthy. So I think that concludes this video. I've covered just about everything. As you can see, the lamp and the voltage source is pretty much 0. See, 1 atto-amp versus 1,000 zeta-amps, whatever that is, not a whole lot. And then the lamp is 324 atto-amps. So, it's not like this circuit wastes energy. Far from it, And if we watch the sine waves, we'll watch that the values here, if you've been looking at it while I've been talking, actually do go down very slowly, but slowly in simulator time, because I had to lower the simulator time to 1 nanosecond in order not to get convergence error messages. So, it's not a good indication of how well you retain your amplitude of driving force, electric force, in cruising mode. I really don't know. I'd have to run this overnight and get an accumulation of seconds here to get an idea of, and then take a screenshot before and after to get an idea how much does this thing run down. I'll have to do that. But first things first, I have to add this circuit button here for little pointers on turning your aerial into a ionic generator, an ion generator. Okay, that should cover just about everything. Thanks for watching.